Okay, yeah. So it's recording. Good. Yes. So yeah. So today we are going to go a bit deeper into some examples. So this is going to be Dedekind zeta function of Gaussian integers. Or Gaussian rationals, doesn't matter. So you remember that what we had was that, so let's recall this from last lecture. For any number field, so a number field was just a finite extension of the field of rational numbers. It is a field which is finite extension of Q. For any number field, we defined a zeta function. I mean, Dedekind defined this zeta function, zeta k of S, because by definition, it's a sum 1 over absolute value of I to the power S, I different from 0. So this sum is over all non-zero ideals in OK, right? And this can be also written as infinite product, like the Euler product formula, 1 minus 1 over absolute value of P to the S inverse over primes. So here, I inside OK ideal. And of course, this P is a prime ideal. And I told you that this follows from unique prime decomposition in OK. That's not a trivial theorem, but we're assuming it. Okay, so then, and this guy, what was absolute value? Do you remember? What was the definition of this? Sorry? Yeah, size of the quotient. Yeah, so just take OK and divide it by I. And this is basically size of this. Yes. Oh, yeah, okay. OK. You remember? Anyone remembers what was OK? Yes. The ring of integers in K, and how was it defined? Yeah. So this basically is equal to the set of all x in K, such that x satisfies a monic polynomial with integer coefficients, xn plus an minus 1, xn minus 1, plus a0 equal to 0, ai belonging to integers. So it's an algebraic number, because this is definition of algebraic numbers exactly. So it's part of algebraic numbers that are in K, in your field, basically. So you can say that's intersection of the infinite dimensional ring of algebraic numbers, all algebraic numbers with K. Yeah.
Are algebraic number solutions to?
Yeah, they are monic. Yeah, solution to monic. Yeah, I believe so.
So let me say, for example, algebra composed over
Oh.
so over they're the same notion, I'm pretty sure, but I think not over.
So maybe you're thinking about the whole field K. Yeah, there are solutions of for example, they come up usually as a set of solutions of any like one equation with rational coefficients. So in that case, yeah, for K you don't need monic, but to be to be algebraic you need monic, right? So, yeah. So but there is a notation. So there is an alternative notation, by the way. It's good to know. And many authors actually use this. What I wrote I, many people just use n of I. I mean, I prefer I. So, but now, so yeah, so we need at least n in some version. So this is the so this is just recall from last lecture. Any other questions you have? Okay. So now let's today we are going to discuss first of all there's this norm map n defined from z of I to z, and I define n of a plus ib is equal to a squared plus b squared. And of course, I mean, here you remember that I also said that O of Gaussian integers Qi is Qi. The ring of integers over Gaussian numbers are just Gaussian numbers with integer coefficients. That's kind of nice. Okay, so that's that's here, this one. So now you can check that, of course, n of 1 is equal to 1, and n of alpha beta is equal to n of alpha, n of beta for all alpha and beta belonging to Gaussian integers, z of I. Yeah.
A squared plus B squared or A squared minus
No, it's a squared plus b squared.
over QI to ZI.
Oh, yeah, it's zi. Yes, of course. This is stupid. Yes, of course. Thank you. Yes, exactly. I said integers, but I wrote QI. Yeah. Good. Yeah. So no, this is so what is that actually? Since you add, that's really equal to a plus ib times a minus ib. That's a plus ib times. Now this now prompts me to give you the general definition. So what is the definition in general? Because there is a way to define. So more generally, this norm map is defined actually from K, from actually, let me put it like this, from OK to Z. How is it defined? It's defined like this. N of alpha is equal to product of G of alpha, but G belongs to Galois group of K over Q. This is a general definition. Now, of course, in this case, you just check that Galois of Qi over Q, what is it? What is the Galois group of Qi over Q? There are only two automorphisms of Qi that preserves Q. There's identity and there's conjugation. There's nothing else because I has to go to something that's a square root of -1, and there are only two options, okay? So that's it. Okay, so this is really Z mod 2Z or Z2. And you can see that this is identity, this is complex conjugation. So this follows this pattern, general definition. Of course, here is more complicated because Galois group in general has finitely many elements. And yeah, you have to check that this is, again, an element of Z, and there are things to worry about. Maybe even we have to assume that K is a Galois extension, but I'm not sure about that, but I don't use it anyhow. Yeah. Question? Yeah, that's right. That's a good point. Actually, yeah, let's not forget that. This is a very important point. Norm is always positive. In general, no, I don't know actually if it is always positive in general. No, it's not actually. No, it's not. No, I mean, so let me give you another example. So now that you ask, you again prompt me to talk a little more. So let's look at another example. What's the other example? Would be, for example, real quadratic extensions. For example, K equal to Q of √2. It's one of the simplest extensions, real quadratic extension you adjoin. So what is the Galois group of K over Q? Sorry?
The identity, there's the one that sends √2 to negative.
To negative. Again, it has two elements, right? And the non-trivial element sends A. And of course, you can, in this case also, it is true that the ring of integers is Z of √2. That's, it's not obvious, but that's true. So from √2b is equal to what? A minus √2b. But now, then what happens to norm of A plus √2b? That's equal to A plus √2b times A minus √2b. That's equal to A2 minus 2b2. And of course, this doesn't have to be positive. Okay? So this negativity of norm, in this case, creates lots of problems, lots of problems. I believe in general, it follows that, well, it doesn't follow, but after some work, you get the experience that maybe imaginary quadratic form, quadratic extensions are easier than real quadratic extensions. It's because of such things. But okay, but we are not going into algebraic number theory anyhow, so I'll just do. Any questions?
Oh, really? I was just going to say the imaginary extension.
Oh, is that right? Okay.
I think so.
Oh, good. That's pretty good. Yeah. Yeah, that's sounds reasonable. Yeah. Okay, so we are there now. So what else I wanted to say? Yeah. So Gauss actually introduced this both Qi and Z of I. So he started doing number theory in Z of I. For him, this Z of I was an extension, but was a new world to do number theory. So one of the first things he wanted to prove was to see if unique factorization theorem is true over there, or for example, if Euclidean algorithm holds here or not. And that's what one of the first things he proved. So let me just write it here, because I'm going to use it. So proposition, this is Gauss. It could be 1830s. He wrote a long paper on biquadratic reciprocity, maybe 1820s, but I'm not sure. So proposition is this, that Z of I, in modern language, we just say Z of I is a Euclidean domain. that is for any alpha and beta belonging to Z of I, beta different from 0, there exists Q and R belonging to Z of I again, such that alpha is equal to Q beta plus R, and this is also important, norm of R is less than norm of beta. So you're just shrinking in length, in a sense. Norm of R is less than norm of beta. I strongly recommend you to sit down and prove this thing for yourself. You have all the tools that you need, more than Gauss had, to prove it. It's a very good exercise. Okay, so we have that, right? Okay, so it's a standard result. I'm going to assume it. The corollary of this is that now Z of Y is a principal ideal domain. Is a PID, i.e., for any ideal I in Z of I, for any ideal I in Z of I is equal to alpha. This is not my notation for principal ideal. So this is, by definition, the set of all alpha X, where X belongs to Z of I. For some alpha in Z of I. Or some alpha belonging to Z of I. The proof is exactly the way you prove Z, for example, is a principal ideal domain using Euclidean algorithm. Yeah, look at your undergraduate algebra course you went through, and yeah, every Euclidean domain is. Huh?
It's been a while.
Yeah. Well, I taught it last year, so I'm still freshman. Yeah. So this is true. And the proof is exactly the same as you do it for Z. You try to find this generator alpha by looking at elements inside the thing with the smallest possible norm. There's one, because they are integer and bigger than or equal to 0, so there is one with the smallest possible norm. You pick that, and that's going to be your generator. Good. So now, it's also easy to see that ideal alpha is equal to ideal alpha prime if and only if, you know, when two principal ideals are the same. It's important to know when two principal ideals are the same. You cannot say alpha is equal to alpha prime. Yeah. They differ by unit, exactly. If and only if alpha is equal to U alpha prime. Oh, yeah, they are associates, yeah. In other words, so for U, where U is a unit. And these are called associate numbers or whatever, but U is a unit. So it then kind of propels us to look at the units, group of units of Z of I. That's also important. That's going to play an important role for us. So what are the units of Z of I? So units of so what are they? Yeah. I. Yeah. So in other words, you can easily check that alpha equal to A plus I beta is a unit if and only if norm of this guy, alpha, is equal to 1. i.e. A2 plus B2 equal to 1, and this is if and only if A equal to plus minus 1, B equal to 0, and A or A equal to 0, B is equal to plus minus 1. So the group of units, there is a notation for it, which is this one. Consists of 1 minus 1, I minus I. So it's an abelian group of order 4, right? How many abelian groups of order 4 we have? 2. Which one of the two this is? Which one is it? There is one, it's called Klein's 4 group, you remember? And the other one, which is cyclic group of order 4. Which one is it? This is a cyclic group of order 4. Yeah, this has a generator I, actually. So this is isomorphic to Z4. It's a cyclic group of order 4. Anyhow, so we have that. So, okay, now I can write down at least one expression for Dedekind zeta function then. So the zeta function of z of I, Gaussian integers. So zk, I mean, remember, this k now is really for us this qi, this Gaussian rational of S. Now, I just write something like this, sum. Okay, I just write double prime, and then I tell you what I mean. 1 over A2 plus B2 to the power S, where, okay, now let me not introduce too much notation. So that's equal to 1/4 of sum 1 over A2 plus B2 to the power S. A and B, the pair AB should be different from pair 0, 0. I put prime here. It means that I'm not summing over all lattice points. I exclude 0. Well, I mean, if it is 0, I cannot even consider that, right? I exclude it. So that's what this prime means. But then I have put 1/4. So why we need 1/4? And first of all, why this is true, and why this? What's the rationale for this quarter? Well, I mean, what was the original notation? I mean, original definition, ZKS was equal to basically sum 1 over absolute value of I to the power S, right? I different from 0. But we know that by this thing, any ideal is principal, right? So I, you can write it as ideal generated by some A plus IB, right? It has some generator. Now, it turns out that norm of this ideal is equal to norm of the generator. This is true. So I'm using that. So it's not totally obvious because you have to go into the quotient of this, measure the size of the quotient, but that's true. So anyhow, so in this case, it happens that absolute value of I is equal to norm of A plus IB. That's equal to A2 plus B2. And of course, I is different from 0 if and only if the pair of integers is not, both of them are not 0. But why I put 1/4? What?
Gauss do it, nobody.
No, Gauss didn't do this. This was by Dedekind. Well, Gauss is student. Gauss. No. I mean, come on. I mean, we are overcounting. Exactly. If I did put that, you see, because I is the ideal, but this is only one element. So you can multiply by any unit and get the same ideal. So we should not do overcounting. Each ideal has 4 representatives. And those representatives all have norm 1, so they don't make any difference, but there's a factor of 4. So I have to divide by 4. So that's important. Okay, are you with me? Now, I want to make a digression to geometry and usual spectral theory, because this quantity also exactly appears in a spectral geometry. So let me just tell you where it comes from in geometry. So you consider a flat torus. So it's a 2-dimensional manifold, which is R2 divided by Z2. We just divide by Z2. And what we do in this case is there is a Laplace operator, Laplacian, that goes from smooth functions of M to itself. I mean, Laplacian is just something like minus d2 dx2 plus d2 dy2. So what are the smooth functions on this manifold M? These are just doubly periodic functions, right? That's what it is. A smooth function which are doubly periodic. And Laplacian is just usual Laplacian because it's flat. That's flat means there's no coefficient here, basically. Okay, so now the spectrum of this guy, of this manifold with respect to this metric and all these things, is the set of all lambda such that Laplacian of f equal to lambda f for some f non-zero. For some f non-zero. It's just like a spectrum of a matrix. That's what it is, right? For a smooth f non-zero. Okay, now you can use a little bit of Fourier series actually to show that a spectrum of this guy actually, what is it? So this is equal to, maybe I have to have this factor 4 pi 2, and then the set of all numbers of the form A2 plus E2, where A and B, belonging to Z. If you, are you with me?
That's true for torus.
That's true for the torus, yeah. It's true for the torus. This is the spectrum of the torus. Now, you can actually convince yourself that these points have to be in the spectrum because there are these eigenfunctions, so f of x and y. I can write it as e to the 2 pi I x plus 2 pi I y. Or actually, I'm going to put something like this. 2 pi I ax plus 2 pi I by for all integers a and b. First of all, these functions are doubly periodic, right? Because if you change x to x plus 1, it doesn't change. A is an integer, and b also is also periodic in y. So, and if you compute Laplacian of this guy, what do you get? If you compute the Laplacian of this function, you get 4 pi squared. I mean, I put minus here, right? So you get 4 pi squared times A2 plus B2. That's the Laplacian. So this immediately shows that at least you have this many points in the spectrum. And then you can use Fourier series information that there can't be anything else. That's it. That's the spectrum. Okay. All right. So now, in general, for any Riemannian manifold, you have this spectral zeta function. So this is yet a kind of a third incarnation of zeta functions now. After Dedekind, after Riemann, this is the third one. Spectral zeta function. So this is like zeta for any compact Riemannian manifold without boundary of S is sum 1 over lambda I to the power S and lambda I positive. Oh, this first appeared in a paper, actually in a Canadian journal, the first issue of, I think, Canadian journal, by two guys, Meenakshi Sundaram and Playel.
Oh, okay.
Yeah. Meenakshi Sundaram was doing this sort of spectral theory, and Playel, I think he was a Swedish. Meenakshi Sundaram was Indian, yeah. Huh?
They come with the
Yeah, they do. Yeah, they proved, yeah, because they wanted to prove Boyle's law for manifolds. And Boyle's technique doesn't work at all, because Boyle was using the fact that this is inside inside Rn and the domain, and you're just chopping the space into different pieces, and then these things doesn't work over manifolds. So they used a much more powerful thing. One of the things they introduced was this function, and they study its properties and its poles in its analytic continuation and this sort of, yeah.
On the spectrum of, on the spectrum are
Yeah, this is a theorem that if you have a compact, in fact, let me just speak closed without boundary Riemannian manifold, let's say oriented, doesn't have to be, then the spectrum, in fact, is just a discrete subset of real line in the positive side, because Laplacian is a positive operator, and it's going to infinity. It's infinite, discrete, and it's going with a certain rate to infinity. And the way that it's, how fast it goes to infinity is Boyle's theorem, Hermann Boyle's.
the density of the
Nothing about the density. We don't know about the density, but about the how fast they grow. That's it. That's the first information. But beyond that, not much is known. Actually, it's a very mysterious set of numbers. Yeah, very mysterious. So what happens in this case is that you see that now, so a spectrum of this torus, except for this 4 pi, or this is really, I mean, basically the same as Dedekind zeta function of this thing. I mean, okay, there is this 4 pi squared, I mean, something which just doesn't matter. I mean, this is very nice because some arithmetic object really comes exactly, zeta function is exactly the same as this geometric object. But I tell you that it's very rare that these spectral zeta functions have some number theory incarnations like this. And vice versa, I'm not sure even all number theory zeta functions are geometric either. I'm not even sure about that. That's a good question to look at. The Riemann zeta function comes from Seeger. Yeah, that's right.
Any other fields, like maybe first or
No, for 3 torus, no, they are not, because we know all these Dedekind zeta functions are defined for real part of S bigger than 1, and they have a pole at S equal to 1. But for 3 torus, they start at they start at 3 over 2, 1.5. They have a pole at 1.5. But these guys will have will be regular at 1.5, yeah. So they can't be. Yeah. There are a lot of differences, yeah. Yeah, since you asked about this, I just wanted to say, look, yeah. Okay. Now, one of the things is, okay, so do you know where this function is convergent? For what values of S is this convergent? What? Real part of S bigger than 1. Why? No, that's not. Yeah, what is it? No, yeah. Yeah, you see, for Riemann zeta function, we had it was not n squared, it was n. But if you're summing over one-dimensional thing, lattice, here you're summing over two-dimensional lattice. So that will create a lot of terms, but it's a squared that compensate for two-dimensionality. So this, I mean, it's not a proof. This is if you want to see. So yeah, how would you prove this, by the way, actually? So the claim. Let me write the claim, and maybe this should be this is calculus. How do you prove that? Convergent for all real part of S bigger than 1.
Related to the harmonic series.
Harmonic series is divergent.
Oh, sorry, not harmonic. No.
Hmm?
Basel series? Over it is.
It's you see, we are summing over integral lattice, right? Except 0, but this means 0 is excluded because I cannot take 0 any. Well, this is related to convergence of a double integral, which would be something like this: 1 over 1 plus. I mean, okay, so I'm going to write something like this: x squared plus y squared to the power s dx dy over absolute value of r. Okay, so again, let me write x2 plus y2 bigger than equal to quarter, for example. So I have a double integral which is defined over. It's just a small circle around 0 I exclude, and the problem is at infinity, obviously, right? The problem of this is at infinity. At 0, I exclude that. You can compute this integral by going into polar coordinates, and then convince yourself that this is convergent if and only if. Okay, so this is less than infinity if and only if real part of S is bigger than 1. This is calculus. That's it. That's the proof. And then, okay, but then you have to compare this with that. Well, you write Riemann sums for this over lattice points and compare it with this. It's exactly like the way we did it for, you can do it for zeta function and using, for example, the p-test for integrals, integral p-test, which is same thing. Yeah, analysis is very respectable field. If you don't like it, that's too bad. That's your problem. Okay, so we have that. All right. Now, so what is the next step? Next step is we want to relate. So, okay, so I mean, this is but we want to relate this to some L functions, the Dirichlet L series, for the actually Galois group of the extension. So this is the next topic, which is very, you see, it is a universal topic. So let me write it like this: factorization of zeta ks in terms of actually L functions. So we are going to show that actually this zeta function it can be written as product of some L functions, and this is typically true. In general, it's true at least for abelian extensions, and for non-abelian extensions, we have to use Dedekind. No, we have to use Artin zeta functions. There will be talk about that. But no. But I mean, let's just go slowly. Then let's not rush ourselves. Just do it slowly. Okay, first of all, we know that zeta k of s, right? I mean, this guy, 1 over a2 plus b2 to the power s, right, is equal to, I mean, this is product of over all primes, right? P to the power s to the power minus 1 and p. So p is a prime ideal, right? P inside I. Oh, shoot. Zeta y prime ideal, right? So then it's very important to know what are the prime ideals in zeta y, right? And that's what Gauss actually studied. So the question is, what are the prime ideals in zeta y? Of course, we know that any ideal, in particular, prime ideals are principal, but they are in zeta y, right? So it's equal to alpha for some alpha belonging to zeta y. But the question is, what are the choices for alpha so that this is a prime, makes it prime? So, any question before is that clear what I'm saying? Good. Okay, good. So now so the way that this goes is like this. We take primes in integers, I mean integral rational primes, in other words, and we look at them as inside zeta y, and we'll see if they stay prime there or not. So that's the start of the game. So take any prime, P belonging to Z. I'm actually positive. I don't want to look at negative ones. Again, equal to 2 each. It doesn't matter. I didn't wrote it wrong, but it's just to be. Okay. So the question is, when T is a prime in Z of y. You see, I mean, the idea is that when you look at this prime inside this bigger ring, the possibility of decomposition is there. It maybe decomposes if you look at it inside, because there are more numbers in Z of y. And that's one of the things, right? Okay, so let's look at the simplest prime, 2, for example. Is it a prime? Look at that. Okay.
Then we can literally I wanted to characterize all the numbers in the I, but even though.
Okay. Okay. Yeah, exactly. Yeah. No, the answer is no. Because 2 can be written as 1 plus I times 1 minus I. 1 plus I times 1 minus I. And this is not a unit. Because we know the units are only just those 4 units we discussed. And it's not a unit. So 2 is not a prime. However, can you write it in a different form, this number? Okay, so I mean, this is good, but I mean, the question is 1 minus I really different prime compared to 1 plus I or not? I mean, so are they associates of each other or not? So what can you say about 1 minus I? If you multiply this one by I, you're going to get 1 minus I. So this is like I times 1 plus I. So actually, this ideal is square of another ideal, which is that ideal is prime. Right? Because this is associate of that. So basically what I'm saying is that now we just discovered that something interesting, that as a prime, 2 is equal to 1 plus I squared. So such primes are called ramified. We say 2 is a ramified prime. When you look at it inside the bigger one, it's really like an image of 2 points coming together. But these two points are like same. And of course, when we say ramified, there is a topological incarnation. You have to have that in mind for ramified coverings and ramified extensions and all these things. But okay, but there is a topological underpinning here, but we cannot, we don't go into that right now. But that's just okay. So that's now other primes. Now, if you have a prime p equal to 4n plus 1 prime. So, because then the other primes, I can write it either as 4n plus 1 or 4n plus 3. You can just write primes in that form, 4n plus 1 or 4n plus 3. It's clear, right? Which are all odd primes are either 4n plus 1 or 4n plus 3. Okay, now, these primes, do you think they remain prime inside Z of I? Oops. Z of I. Well, this question is not a fair question. I realize. I mean, asking you this question is not fair. It's just a way of talking. I don't expect you to you do it because because the answer relies on a very important theorem that was proved by Fermat. Fermat showed that any number of the form 4n plus 1 is a sum of 2 squares. I mean, of course, integers, right? So Fermat, any prime of the form E equal to 4n plus 1 is equal to A2 plus B2 for some A integers A and B. A and B belonging to Z. This is not an obvious theorem. I mean, it needs a proof and it's not trivial. Okay, so if you use this theorem of Fermat, then what can you say? You can just say that, okay, P then is equal to A plus IB times A minus IB. And these two primes are not associates of each other. This is not I times the other one. You can convince yourself, or minus I times. They are not associated. So these are, but they are primes. They're distinct primes. Okay. Okay, so then the prime P, the ideal P is equal to ideal A plus IB times ideal A minus IB. So these primes, I believe they are called the split primes. So they just divide into two pieces. So they are split primes. Okay, so we discussed the fate of these primes, and only another group remains, which is 4n plus 3. And of course, 4n plus 3 is not sum of two squares. Why? Is not a sum of two squares. How can we? Sorry?
At least 3 is not sum of.
3 is not sum of two squares. 7 is not sum of two squares, and these sort of things. Is there a quick proof that why this is not sum of two squares?
Well,
what?
Check small enough.
Yeah. You're not going to get that 3, right? I think this is elementary, actually. It's you just do two cases. Yeah, I thought so. I mean, because I have thought about it some time ago, not before the class, but long time ago. I convinced myself that's elementary. So this is okay. So and it turns out that these guys actually remain prime inside, and in fact, they remain prime in Z of I. So I mean prime ideals in Z of I. And so I won't go into that because it takes some time, I believe. You can show that actually these are all the prime ideals of Z of I. So, and with a bit more work, can be shown that these are all the prime ideals of Z of I. So what happens? There is a very nice geometric picture actually now. So we can list all prime ideals here. So it starts with 2. What's the next one? 3. 3 is I just write it here. 3. 5, but 5 is not prime in Z of I. 2, yeah, you're right. 2 is not a prime. 2 plus I, 2 plus I is the prime, right? No, 1 plus I, sorry. 1 plus I, yeah. 1 plus I is the prime ideal. I mean, ideal generated by this prime, yeah, thank you, yeah, good. But 3 itself is a prime. 5 is not a prime, but it gives us 2 primes. What? 2 plus I and 2 minus I. Oh, how do we know these are primes? Oh, yeah, this is easy. That's my answer. That was a good question, but my answer is even better. That's easy. Use norm and the fact that this guy is a prime. And if, yeah, okay, so that, okay. So the other one is like 2 plus I and 2 minus I. What is the next one? So this corresponds to 5. What about 7? 7 remains prime, right? 9 is not a prime, 10 is not a prime, 11. What about 11? Huh? Say it a little slower. Yeah, it's what? 2 plus 3i, you mean, and 2 minus 3i. You're talking about primes inside. 4 plus 9, oh, that's 13. No. What about 11? Huh? 11? Oh, 11 is prime because I can take it. Yeah. So it stays prime. Okay, good. Okay. But 13 is what I said. 2 plus 3i and 2 minus 3i. You see, you can write it as 3 plus 2i also and 3 minus 2i, things like that, because they are associates. The ideals don't matter, don't change. It's just a representative of ideals. So what about the next one? So after 13, 14 is not a prime, 15 is not a 16. What about 17? 17 is 4n plus 1, 16 plus 1. So is not a prime. How can you decompose 17? Would be what? Well, how about 4 plus I and 4 minus I? We get us 4 plus I and 4 minus I. Okay, so this is the situation in Z of I. Now, what is the situation in Z? Well, I mean, here there is 2, there is 3. These 2 points map into 1 point. This is 5. This is 7. This is 11. This is 13. This is 17, and so on. And you can think of there is a map here. Sends these 2 points to 1 point. So it's like a covering space of this one. It was these points, things go wrong. They're like 2 to 1, but at these points, actually, this is really worst point in a way, because really 2 points kind of stick together here. This is, yeah, anyhow. So you're squaring here, but here you're, okay, now this guy has a name. This is called the spec of Z of I. And this is called the spec of Z. So what is a spec? As you know, this is the all prime ideals of a ring. So if you have any commutative unital ring, right? Yeah, so you know that. Yeah, for any commutative unital, I mean, it has a unit. Because I come from analysis, so for me, a unit is not necessary. It's you have to assume. But I mean, in algebra, people anyhow. So for any commutative unital ring, A, spec A is the set of all P inside A. It's a P prime ideal. Okay, I mean, the spec is more than just a set. So the way I define it is just a set, but there's a topology on the spec. It's called Zariski topology, and there's also a sheaf of rings, local rings over spec. There is some structure. And also, another thing is that the spec is a functor. So you get a functor from rings. So this is the spec functor. It goes from rings to, who likes sheaves here? You like sheaves? To sheaves. Huh? Huh? Yeah. Yeah. Up. Goes into sheaves. Sheaves. Sheaves of local rings. Let me give you a little more. Sheaves of local rings. And what this picture really refers to, where this picture comes from. Now you see where this picture comes from. This picture comes from, can you tell me where it comes from, actually? From this functoriality? Huh?
What is the opposite?
Oh, this is the opposite category. Category of commutative rings, okay? Okay, so let me explain this this thing. So if you have a map F from A to B, just a ring map, right? Ring map. Ring homomorphism, in other words. You get a map, pull back from a spec B to a spec A. By the following, you just send prime ideal P to F inverse of, you just check that this is a prime ideal again, and da da da. And this is functorial. Okay, you have to also observe that there's a sheaf here, and this also acts on sections of the sheaf and all this thing, but that's okay for now. That's what, okay, now this comes from the natural embedding of Z in Z of I. You get a map from spec Z of I to spec Z, and I'm saying that this corresponds to this map that we constructed here. So this is an attempt, a first attempt, to geometrize arithmetic. So now we have this arithmetic situation. Now we are beginning to geometrizing it. We are beginning to think of rings as spaces. Actually, spaces of functions on some space. That's what. And this is a very, very useful, powerful idea. And that's basically the only way that many, many results in number theory can be proved, by geometrizing things like this. It's the first step. It's the first step. So what we're going to do now, we're going to take a break, because now I'm going to use this. This is a very valuable information. I'm going to use this to write down the factorization of the zeta function in terms of L functions. So let's now see where we are. Doesn't want to end. It's very stubborn, or doesn't like me at all. Oh, no. I made a mistake, actually. It's good that I was, oh gosh, I should pause it. I was just ending it. Then that would be terrible. Actually, it's good that it didn't respect me. Yeah. Pause, come on. Nathan, I think you have to come.
Pull from the right.
This one?
Not yet, pull that right out.
And that would do it?
Then it'll go. What up?
No, I don't dare to.
Yeah, they care.
Still recording.
Give it a sec. Now.
So we are recording. Yes. So what?
Interesting strategy.
Start video. Yeah. Okay. Okay, guys. So you're on camera now. No, you're not. You're not. Okay. So now let's use this to finally compute this zeta function, factorization of the zeta function now. So, okay, now we can just say, well, zeta k of s, of course, is always product. Again, I just write it many times, 1 over absolute value of p to the s. This 1 over p. Now, so we have to go to list of primes here and multiply this Euler factors for all those primes. So we have to compute absolute value of the p for all those primes and just take it. Okay, the first one, of course, is 2 here. I mean, norm of this is 2. So this is equal to 1 minus 1 over 2 to the s minus 1 times product of 1 minus p to the power minus 2s minus 1. Okay, let me write it here in a better, more coherent 2 to the minus s minus 1. This one, p is equal to 3 mod 4 times product of 1 minus p to the minus s minus 1, p equal to 1 mod 4, again times product of 1 minus p to the minus s minus 1. I hope this is inside camera. P equal to 1 mod 4. Yeah. Here. Yeah, why is that negative 2s? Yes. I'm asking you. Well, I don't expect you to answer. Others.
It doesn't split.
Yeah, these are the ones that they don't split. So it's there. P is a prime. If a prime is of the form 3 mod 4, it doesn't split. So its norm is p squared. For norm of what is norm of p? It's p squared. So you get p squared factor. I already calculated that. So no, I'm not writing ideal here. I'm writing number p now. P is a prime, but this is an ideal. This is generated by that prime. I'm using different notation now. Okay, and for these ones, they split. You know, a plus ib and a minus ib kind of thing, and each of them now has norm p actually. You see. That's the reason that we have that sort of decomposition. Okay, now what we can do, I can take this bit with this bit. Oh yeah, so let me write it again before going too fast. 1 minus 2 to the minus s minus 1. Product of course, I can write this as 1 minus p to the minus s, right? 1 minus p to the minus s minus 1 over p equal to 3 mod 4 times product of 1 plus p to the minus s minus 1, p equal to 3 mod 4. See, 1 minus p2, I just write 1 minus p times 1 plus p, and yes. And then here, product of 1 minus p to the minus s minus 1, product of 1 minus p to the minus s minus 1. This is doubles, so this is p equal to mod 4, 1 mod 4, sorry. And p is equal to 1 mod 4. I just decompose this as 1 plus p times 1 minus p, that's it. Okay? So I just split everything now. So now I just take this part together with this part, together with this, 1 mod 4, one factor here. What do you see here? If I multiply these factors with this factor, with this factor, what do you get? That's the Euler factorization of the Riemann zeta function. So this comes, so this times that is this zeta function of the Q actually, right? So that's equal, because according to our formula, the zeta function of Q is a Riemann zeta, which is, I want to write zeta Q, just now emphasizing that, right? This is Riemann zeta, yeah. Riemann zeta. Okay, now these two pieces I can keep. I just write product of 1 minus, or rather 1 plus p to the minus s minus 1 times product of 1 minus p to the minus s inverse. Here is p equal to 3 mod 4. And here p is equal to 1 mod 4. 1 mod 4. Is that clear? Okay, good. So now I can write this in a different form, which is more illuminating and perhaps will remind you of something. I can now write this as zeta q of s times product of 1 minus chi p to the s inverse over all primes, where chi is defined as chi p equal to 1 if p is equal to 1 mod 4 and chi p equal to minus 1 if p is equal to 3 mod 4. And of course, the rest are 0. And it's 0 on the rest of our things. And 3 mod 4, you get negative and positive. So this is definitely correct. Now, can you tell me that this chi is a Dirichlet character or not? So that's the question. So is chi a Dirichlet character? And oh, what? What is it? I thought we settled with them. I don't know why they are just, what they're just encroaching on us. I mean,
They're very fair. Always hovering there, trying to take this room.
exactly. I mean, I don't know. It's so many rooms. I don't know why. What's the interest?
I think you should want that. We close that one, we lock it.
Yeah.
We can look at the other one there.
Yes, exactly. Yeah. Yeah. Yeah.
Same product. What?
Yes. This product twice. Which one? This one. Yeah, because these are the split primes.
Yes.
You see, 8 when p is equal to 4n plus 1, it's of the form a2 plus b2. Then it can be written as a plus ib times a minus ib. But those are still primes in the big one, in the zi. Yeah, they're distinct primes. There's a duplication. It's like a, so at this point, it's like a twofold covering, honest twofold covering. Two different points upstairs come to the point. But yeah, okay. Sorry? Oh, -2? Yeah. Yeah, we can. But I mean, I wanted to take one copy of this, mixing with that and that. Yeah. So that I needed the splitting, really. Okay, so now, in fact, chi is the Dirichlet character. Yes. Chi is the Dirichlet character. So if you look at z over 4z, this one, which has only two generators, 1, 3. So this is, of course, isomorphic to cyclic group of order 2. And we know that it has only one non-trivial character, right? And this chi is the non-trivial character that sends 3 to -1. Because this 3 is generator here. So chi is the only non-trivial character here. Non-trivial character. Okay, so then we know that. So this is a Dirichlet character. But now, question, yes.
Where did
Z mod 4Z. Well, I mean, oh, you mean, what do you mean exactly? Yeah, it comes from someone's brain. No, I mean, that's a good question. I agree. I mean, I was going to say it's the Galois group, but it's not, because the Galois group is Z2. So this is the group of units, but I don't see exactly why the group of units should play a role. So I was thinking about two answers already, but both of them are wrong, it seems to me. So I just don't know. That's a good question. Yeah. But mathematically, it's correct what we wrote, of course. Yeah. Yeah, that's right. No. He wants to have to know some higher reason why this is true. And that's a good question. Yeah. No, it's not a question of truth. It's a question of why or where it comes from. Is more idea.
Where,
Sorry?
we're in mod.
What do you mean we are in mod 4? What is mod 4, huh?
We're thinking about primes.
Yeah.
And if you multiply.
Prime is mod 4, yeah. Yeah, I mean, no, I mean, those things I know, but I want to give an answer which would work in more general settings that I'm not sure. Yeah, I will give an example on that. That's right. But the thing is, this group is exactly a Dirichlet character of this. Is just, I mean, this 4. Okay. I'm not satisfied with these answers anyhow. Let me put it this way. I still want to think about a better answer. Yeah. Okay, but now, huh? Yeah. It's all here, but it's in my mind is now all mixed up completely. So I better say nothing to not to confuse you. But it's easy check. Once we are told, we can check. That's what it is. Okay, now, so this is a Dirichlet character, so it's completely multiplicative, right? So chi is completely multiplicative. I mean, it's fully multiplicative. Multiplicative. So we know that then a product of 1 minus chi p over p to the s inverse over p for all Dirichlet characters, like this is L of s and chi. So now we are going back to beginning of the course. We can write it as also as a sum, right? Because there is an Euler product formula. This is sum chi n to the s, and from 1 to infinity, right? So this factor then that we had, so this is, in this case, of course, becomes equal to 1 over 1 to the s minus 1 over 3 to the s plus 1 over 5 to the s minus 1 over 7 to the s plus 1 over 9 to the s minus 1 over 11 to the s. I don't know why I like to write it down forever. It's a kind of good habit. I mean, just sort of gives yourself some time to relax. So this is really the second factor. This is the second factor. So what we discovered so far is that, yes, this zeta function of our number field, Gaussian rationals, S is equal to Z Q of S times L of S and chi. Chi is a non-trivial character mod 4. Chi is a non-trivial, that's the important thing, character mod 4. I mean, when I was writing these things, I assumed n to be the modulus, and then characters mod n I was working and I introduced, but this is n is equal to 4 in this case. Okay, now, what do we know about this? First of all, this function is what? Is holomorphic at s equal to 1, this function. Because I proved in general that for any non-trivial character, the L function is regular at s equal to 1. There's no pole at s equal to 1. I mean, in this case, you can just see it with your own naked eye, because this is an alternating series and this is da-da-da. This is fine. But zeta, Riemann zeta, gives it a simple pole at s equal to 1. So then it follows that this zeta function of Gaussians has a simple pole at s equal to 1. And its residue is this number. Oh, yes.
You know that number?
Yes. You know, I will calculate it now. Question? No, okay. I said, I won't write zeta by, because that creates an ugly picture here. I am assuming in this lecture, k is equal to q of I. Or, yeah. I said Gaussian integers many times. Yeah. Yes. Okay. So ZKS has a simple pole at s equal to 1 with residue. Well, I mean, the residue we can compute. I mean, the residue is this number equal to 1 minus 1 over 3 plus 1 over 5 plus minus 1 over 7. This is just alternating sums of all odd numbers. All odds. They're not primes, they're just odd numbers. Yeah, plus 1 over 9. This is the residue. Have you seen this number before? What's that number? Again, this is not a fair question. I mean, you have seen it. I mean, you have calculated perhaps in calculus courses, but there's no reason. Sine. But sine doesn't have factorials. So there are no factorials here. So what is this number? Well, this number, I believe, is equal to pi over 4. So lemma minus 1 to the n over 2n plus 1, and from 0 up to infinity is equal to pi over 4. Proof. How can we prove this? We can use integral 0 to infinity dx over 1 plus x squared. Let's compute this number. Dx over 1 plus x squared. What's that integral? Well, this is calculus. You're TAing calculus course perhaps right now. So you have no excuse. You have to know this. Right? So what is that? What is antiderivative of 1 over 1 plus x squared, guys? Huh? Tan inverse of x. Arctan, yeah. From 0 to infinity. So what is tan inverse of infinity? Pi over 2. So this guy is just. Are you with me now? Are you okay? Now what is okay? So this integral is definitely pi over 2. But why this integral is related to this? Well, how about I use geometric series to expand this? Doesn't make sense. No, I cannot use geometric series because that would give us x, and an integral of 0 to infinity of x is. So what can I do? Huh? I see. Riemann sum? Let's see. I mean, I thought the proof I should not look at my notes even. Do I have? I hope I have a proof something. Oh gosh. Oh no. Sorry. I don't want to go to infinity. I want to go to 1. What about 0 to 1? What's the tan inverse of infinity? Well, I mean, so let's compute it to 1. Huh? Tan inverse of, let's compute it from 0 to 1. What is tan inverse of 1? Pi over 4. Tan inverse of 1 is pi over 4, guys. I mean. But now let's write this as, but also left-hand side is equal to, so let's expand it by geometric series. So this is 0 to 1, sum. Huh? What I did? Oh, shoot, 0 to 1. I don't know why, it just, maybe this is something I have. 0 to 1, sigma. What is this geometric series? This is 1 minus x squared plus x4, and so on. So 1 minus x squared plus x4 minus x6, and so on, right? Dx. Oh, there's no sigma there. Stupid. Okay, now let's compute that. So let's compute it. So we get okay, so I mean the antiderivative. So for the first one, I've got x, which is giving me a 1, right? Which is 1. And the next one, I get minus 1/3 plus 1/5 minus 1/7. So we just integrate term by term. About the swap, yeah, I was just thinking about that, if it is legit or not. Are we cheating here or not? I mean, I think it's okay, but I mean, although, I mean, we are really at the verge of convergence of the series. You see, this is at 1, this is divergent. So there is some funny business going on. So you have to be careful about the validity of the argument, but I think it's correct. I don't want you know, to cheat or anything. I just tell you that there is some issue to handle. And that's yeah, but this is okay. I believe this is okay. I don't know, maybe you have to use Lobeck dominated convergence theorem, which is I always, yeah. Okay, so this is pi over 4. So the residue then, so we arrive at this formula, residue of zeta of, just for you to make you happy, qi of s at s equal to 1 is equal to pi over 4. Although, I mean, there is something here we have to be careful. These, so yeah, because there was a 1/4 factor, but I directly work with primes in this case. So this is okay. So this is okay. I'm not using, so this is pi over 4. I believe this is correct. So now what we want to do, which I will do it next lecture, is the following. There is a magnificent formula. It's called Dirichlet's class number formula. Okay, so this Dirichlet class number formula is like this. First of all, this story that we are doing here is true for all number fields. Okay, first of all, this is zeta k s for all number fields k as a simple pole at s equal to 1, and its residue, there is a general formula. I mean, okay, I'm not sure the most general case was proved by Dirichlet himself or not, but certainly he had it for quadratic extensions, definitely. And its residue is given by so this is the formula. So let me just write it completely in a nice way. So yeah, residue of zeta k s at s equal to 1 is equal to 2 to the power r1 2 pi to the power R2 times h of k times r of k divided by wk square root of absolute value of dk. Huh? Is that good enough? Yeah, I get it. I guess. Yeah. Right. So what are the things involved here? First of all, where k over q, the degree of extension is equal to, which is equal to n, is equal to R1 plus 2R2. R1 is the number of real embeddings of k. I mean, distinct, of course, real embeddings of k. And the 2R2, or rather R2, is the number of complex embeddings of k divided by 2. Just this number is always even. This number of complex embeddings is always even. You divide it by 2, you get R2. So if you want, you can say 2R2 is the number of complex embeddings. Okay, dk is the discriminant of the extension. dk is the discriminant. I will define this discriminant of the extension. Wk is the number of roots of unity in k. Is the order of groups of roots of unity in k. The number of roots of unity. Because roots of unity in any ring is a group, and then this is a finite group. You can check, and this is what it is. Now, what about hk? So hk is equal to class number of k, which is the order of ideal class group. Order of ideal class group. And Rk is the regulator. I will define this Rk regulator of K. This is basically volume of some parallel pipe inside the lattice of integers inside K, inside OK. Yeah, so I defined all the terms over there. Yeah. So what we're going to do now is we are going to, so I still have to define some of these terms, like R1, R2. But I mean, this is, let's settle this before we leave. R1 is clear what it is. Number of real embeddings of K, but real embedding means that number of embeddings that you can put K inside R. For example, for Z of I, what is R1 for Z of I? 0. There are no embeddings in real numbers, so that's 0. And what is R2 for Z of I? Complex embeddings. There are 2, because I can go either to I or minus I, and this would be an embedding again. Yeah? So that's now dk discriminant. I will define it. This is clear. Class number basically is a group that controls how unique factorization fails inside inside the ring. Unique factorization in terms of numbers, not ideals. For ideals, it's true, but Well, it fails. In how many different ways fails? This is. So it has to be defined. Okay, I'll define it. And regulator is a certain volume, is a determinant that I will define. But so yeah, this is should be one of your most beautiful formula in mathematics that has been put forward in 19th century. So yeah, it has that sort of flavor. Yeah, it has a sort of. I agree. Yeah, it's kind of. So Dirichlet apparently had this for quadratic extensions. Actually, could be even for quadratic forms in that context. They were not working in the context of number fields. It was Dedekind who switched the gear to number fields in a sense. So, but I don't know, maybe Dedekind, I don't think Dedekind even had it. It could be that this is in even 20th century. Eke proved it in general. It could be. I'm not sure. I don't know the history. Huh? Yeah, this one has only one pole. Yeah. Simple pole and residue. So residue detects something. So what we are going to do, we are going to check this for our zeta function. So when you calculate all these things, we'll see that it checks for our zeta function. And my next topic is going to be to look at the zeta function for cyclotomic fields and see what happens to those. Because that's kind of, yeah, then you see some features because that's related to quadratic, that's related to reciprocity laws and this sort of things. Okay, but, okay, so something happened here. It's gone out of sight now. Maybe it's working still. Oh, no, it's working. No, I just stop it now. So I end it.